by 2 ANOVA. And what we've seen so far is the additive model. What is known as the additive model, where we have a parameter modeling the expected value in the combination of the first level of the first factor and the first level of the second factor. Then the difference that is associated with going from the first level to the second level of the first factor, and the difference that is associated from going from the first level of the second factor to the second level of the second factor. Now, if you have this model, which we also then, of course, looked at in terms of its design matrix, which looks something like essentially this, with some irregularity things here. If you have this as your x and your beta, and you now estimate beta based on, of course, the standard Gauss-Markov beta estimate, then, of course, you can, if you then do t-tests by introducing some linear contrast weight vector, for example, 1, 0, 0, or 0, 1, 0, or 0, 0, 1, you cannot test, or you have no means to assess an interaction because you did not model an interaction. You just modeled additive effects given by each of the alpha 2 and beta 2, but there is no interaction effect in there that you can now assess. So if you have some program that gives you out the effect of an interaction and whether it's significant, the interaction has always been modeled. That's kind of the point. And this modeling of the interaction in a 2x2 ANOVA, that's then what I want to do next. So we basically, just get rid of that like this. We extend now the 2x2 ANOVA model with an interaction that is explicitly modeled. Of course, and of course this is all on the road towards PPI, where of course there's also an interaction modeled, otherwise it wouldn't be called psychophysiological interaction. Now, again, we only have 4 cells, so we have expected values for I and j in a 2x2 setting going from 1 to 2, and j going from 1 to 2. And if we represent them again in this tabular way, where we have j going over columns and I going over rows, like this, whatever, then the idea of now modeling interactions is as follows. So for our mu11, the basic idea is to have an offset, to have the effect of the, make it clear, to have the effect of the first level of the first vector, so alpha 1, the first level of the second factor, and a term that models the contribution of the specific combination of the first level of the first factor and the first level of the second factor. Yeah. So I need a bigger table, so I'm creating more space. So essentially this is the new term here. So alpha beta 1 1, or in general alpha beta ij, that's the interaction effect. The this is not something about multiplying alpha or beta, so in general one could have just, of course, taking a gamma, so that would also work, alpha, beta, gamma, 1, 1 as the interaction effect. The alpha, beta is nice, so that one knows that this is about combining alpha and beta, but it's just a symbol. It's not a mathematical operation, and these brackets are not for mathematical reasons. It's just notation. So that would be the general idea of modeling the expected effect for one of the cells in a 2x2 ANOVA design with interaction, and of course this then is done a similar way for the other expectations. So here we would have alpha 1 plus beta 2 plus the effect that results from the combination of the first level of the first factor and the second level of the second factor. So that would be like this. How do we do that here? Maybe we do I equals 1. No. J equals 1. J equals 1. J equals 2. And here we have I, that's our row factor, I equals 1 and I equals 2. Same for the expected value of the combination of the second level of the first factor and the first level of the second factor. That would be mu0 plus now alpha 2 plus beta 1 and the interaction effect. And finally, for the last one, now of course, in a way you know the drill by now. This is of course many times over parameterized, because we have 4 values of interest that we want to model, namely the expected values in each of the 4 cells. And we now use how many? I mean, there are alpha 1 and 2, beta 1 and 2, so 4 plus for interaction terms. We use 8 values to describe them. Of course, there are many 8 values that can describe these 4 values. So the way to deal with that is again the reference cell formulation. And here the reference cell formulation takes the following form. One sets everything that has a 1 in it to 0. So alpha 1 is set to 0, so we get rid of alpha 1. Beta 1 is set to 0, so we get rid of beta 1, and alpha beta 1 1, alpha beta 1 2, and alpha beta 2 1. They are all set to 0. Yeah? What we didn't do right now was to write this in design matrix formulation. That's a nice exercise that you can do at home. Of course, it works exactly as we translated previously the effect size combinations, or the effect combinations into expected values by means of the appropriate design matrix. We skip this step now because it's just essentially writing business, and focus then on the design matrix formulation of this. So now if one looks at what happens then in terms of the expected values of the 4 cells of the 2x2 design, we get mu1 1 being mu0, yeah, because all the rest is set to 0 or constrained to be 0. Mu1 2, we have mu0 plus beta 2. Mu2 1, we have mu0 plus alpha 2, and mu2 2, we have mu0 plus alpha 2 plus beta 2 plus alpha beta 2 2. So that's then the formulation of the expected values for the 2x2 ANOVA design with interaction. So what do we see? Now if we go over, let's say, from over levels of the column factor, so if we start here, J1, and look then what we have at J2, we see that the expected value that we have here and here and here and here depends on the row factor. So if we go from here to here, we have an additive term of beta 2. That was like in the additive version. But now, if we do this not for I being 1, so for the first level of the row factor, but for I being 2, so for the second level of the row factor, then we have the additive effect of beta 2. So mu0 plus alpha 2, mu0 plus alpha 2 we have here as well. We have beta 2 in addition, like we have at the first level, but we also have alpha beta 2 too. So the effect prediction for the column factor now depends on the levels of the row factor. And similarly the other way around. So if we go down the row factor, we see that we have here the effect of alpha 2 and so we have here the effect of alpha 2. We also have here the effect of alpha 2, which is added to the expectation that we have already. So here mu0 and here mu0 beta 2. And then depending on the level of the column factor, we have either an additional effect of alpha beta 2 or not. Yeah? So this is how this idea of an interaction, so that the expected value for one level depends on the level of the other factor that you are of course familiar from looking at the bars or looking at these strange plots in SPSS. They are not that strange, but this I guess you've seen. We've seen this for 2x2 ANOVA. Yeah. How this is translated to the modeling business in terms of the GLM. Now the final thing is to write this in design matrix form. So again, of course, our Y is just our data points written below each other. So I do it anyway. So, start with 1, with the final one. So this is again just putting the data into a column vector format. And concentration is going down. And the parameters that we are left with, so this is what a menu trick for big vectors works. Our parameter vector now has our mu0, our alpha 2, and our alpha beta 2. So that's our beta parameter vector, and now the final thing is, of course, to put to create the design matrix that implements what we have there. So anyway, I do it. It's I think you can do it, so that's not really helpful to ask you. So mu11 needs the mu0 only, so it has zeros for the remaining ones. And then we leave step 3 and do mu1, 2 has the mu0 and the beta 2, so it has 1, 0, 1. Mu2, 1 has mu0 and alpha 2, so it has 1, 1, 0, 0. So that's mu2, 1. And finally mu2, 2 has all of, no. 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 I'm confused. No. No, it's fine. So, this is what we want to create with our design matrix and our vector. And this is then the design matrix. So you see basically this kind of pattern in terms of the design matrix. So one column of ones, then the ones for the main effects, like this. And then the question always arises is, how do you create, because these are of course the regressors in a design matrix, how do you create the regressor for the interaction? And the rule of thumb, or I don't know how to call it, the way to memorize that, or whatever, is you multiply the main effect columns of your two main effects in a column-wise manner. So, in an element-wise manner. So you multiply 0 times 0, then you get 0. 0 times 1, then you get 0. 1 times 0, then you get 0. And 1 times 1, then you get 1. So you only have ones down here. So that is something that you read sometimes, that you form the interaction by multiplying the columns of the design matrix. Somehow I never fully understood what this is supposed to mean. The way I look at this is that right now is that it looks like that, but actually it just falls out by modeling an interaction effect as the specific contribution due to a specific combination of column and row factor, so of these things, and then using the reference cell formulation. And then you get to a design matrix pattern that looks like you multiplied this and this column, but in fact it results from throwing out many of these columns that were in there before, like the alpha beta 1 1, alpha beta 1 2, alpha beta 2 1. So in any case, that's then how the design matrix formulation of a 2x2 ANOVA with interaction looks like. Yeah.
And just to be sure that I understood it correctly, are the 4 different groups that result from a combination of the two vectors represented in the rows, in that sense that the first quarter is the first group, and N1, for example, is the number of samples or of participants in this first group, and N1, 2 is the number of participants in the... Exactly. Okay.
Yeah, that's kind of the, if one wants to model many different designs, like simple linear regression, 2x2 ANOVA with interaction and so on, that per se somehow have different data representations. So for simple linear regression, you would think you have something like x and y, and then you have a table of your x values and your y values. And for 2 by 2, you have these 4 cells and so on. So one thing that, of course, helps a lot to harmonize these things is to always organize the data in the same way, namely as a one big vector. And then, of course, it's important how the data points are ordered in this vector. So, of course, the design matrix, if you now mess up the data in here, so you randomly exchange data points and you keep the same design matrix, then, of course, the whole thing doesn't make sense anymore. So the data organization and the design matrix organization, of course, need to be aligned. Yeah. Good, but with this, then one can test for, so based on the estimates of alpha 2 and beta 2, one can test for significant main effects, and for with the estimate of this alpha beta 2, one can test for significant interaction. And if one plays around, which I think will be one of the programming exercises in the summer term, if one plays around with these parameters, one can create, and this is fairly instructive actually, one can create many of these patterns here. Not many, but all of the patterns that one is interested in. Yeah. So that would be modeling a 2 by 2 ANOVA with interaction and then assessing the significant main effects and interactions using the machinery of the GLM. Now we have how much time left? Let's have a look. A little bit time left. Now we are almost there with PPI, but not quite, because PPI refers to not an ANOVA design that is modeled with interaction, but an ANCOVA design with interaction. So we now can move on from, or have to move on from ANOVA to ANCOVA. And the thing about ANCOVA is that in contrast to simple linear regression or multiple linear regression, so remember that when we discussed the GLM, we discussed multiple linear regression. Let me briefly remind you of that. So we did something like this. Let's do it like this. So that was our multiple linear regression that we used in our case all the time for first level fMRI models, where our axes were then what? What were the axes in our application of multiple linear regression to fMRI data? Yeah, but how did we create them? Or what was it? No, these were actually not 1 and 0s. So think of how did the design matrix for first level fMRI look? So this was all the business that we discussed for in terms of convolution. So these were the axes, so multiple linear regression in the sense that we have continuous regressors. So continuous. So the reason why I'm bringing this up and how I got there was that ANCOVA is a combination of regression designs or continuous designs, like our multiple linear regression that we use for fMRI, and categorical factorial designs. And that's the characterizing feature of ANCOVA designs. So the easiest to think about or to associate with that is that for ANCOVA designs in the design matrix, you don't have only ones and zeros like in ANOVA type designs, and you not only have continuous numbers like in regression-like designs, which is not quite true in regression-like designs because usually you also model the offset, so you also have this one column in there that only has ones, which is like actually in the discrete categorical design thing. But in ANCOVA you have both dummy variables like these ones and zeros that we've now seen for ANOVA quite a lot, and regression-like columns like you have in the case of multiple or simple linear regression. Yeah, so that's the characterizing feature of ANCOVA designs. Yeah, and of course, to get started with that, it helps to again think of how the expected values of different groups are formed, because there are groups, because there is this notion of a categorical factor, and then also see where the regression type thing comes in. So with ANCOVA models, you can of course combine many discrete factors with many levels, with many continuous factors or continuous regressors. We focus on the case that we have one categorical factor and one continuous factor. Yeah. So I'm using the word continuous factor now, which may or may not make sense to you, but I think it good, at least the learning outcome is that if you kind of start thinking about factors a little bit more flexible in the sense that they can be either continuous or discrete. So I'm referring to regressors now in our design matrix that have continuous values in them also as continuous factors. An example that I use in the script is the case of this data set with old and young participants who drink different amounts of alcohol. And one looks at their brain volume. So the outcome measure, so as an exemplary data sets for ANCOVA, an outcome measure could be DLPFC volume. And then, how do we do it? Not there. Then we look at two groups. We look at a young group and we look at an old group. So a group of old participants and a group of young participants. We look at their DLPFC volume. Maybe not, let's put that here. And for each of these outcome measures, so I'm just making up some values here. We also, no, the table is too big. We also have a continuous experimental or independent variable, namely the alcohol intake. So in units of alcohol or whatever, so we have something like this. Yeah, so there is this notion of a discrete factor, which is here the column factor, which has two levels, namely young and old, and so that's kind of discrete. And we have a continuous factor, which is the alcohol intake, which is continuously varying with the experimental unit. And each experimental unit has, so each participant here has one outcome measure, namely the DLPFC volume. So these are our data points. Good. So how much do I want to still do? Yeah, I think this we can do, and then we stop it there. So again, it's helpful to adapt the notation. So our data points are these things here. These are our Yij. Now label S by I the levels of the discrete factor, so that can be 1 and 2 for young and old. And J, just indexing the number or the number of the data point within the ith group. Yeah, so participant in ith group. And then the idea is again to now assume a univariate Gaussian for each of these data points. So assume that these are the realizations of univariate Gaussian random variables that have a data point specific mean. So mu ij is now data point specific. It's not group specific. And the fundamental idea is to create these data point specific expected values by the combination, of course, of an offset, but then of a, how do I call it here? Factor level? Discrete factor level. Effect plus the contribution of the ijth, that's the ijth independent continuous variable, so alcohol, multiplied by a slope parameter. So if you think back in terms of the multiple linear regression, there we had a lot of these x's and betas. So xi1, beta 1. Here I now put the beta 1 in front, but that's, I leave it now as this. That's fine. Here we only have one x, so we don't label the x's. In addition to what we have in multiple linear regression, we have these discrete factors. And the other way around, in the ANOVA type of things, we only had these discrete factors and we didn't have these kind of independent continuous independent continuous experimental variables. Yeah? And how this is then transferred into design matrix and how interactions are put in, this is then what we do next week. Because this is exactly what's happening in PPI. So next week, once we went over ANCOVA, we have established PPI. Yeah? Only that the x's and the ones in the design matrix assume a very specific interpretation when we use ANCOVA designs with interactions as PPIs in brain imaging. So now I am exhausted. Any question? No. Good. Then let's stop here and continue next week.